In this video, we will look at a related rates question that involves a circular area. So in this question, we've got bacteria producing in concentric rings on a petri dish. The circular area occupied by the bacteria is increasing at a rate of 3 square centimeters per day. When the radius of the outer ring is 4 centimeters, we want to know at what rate is the radius of the circular area changing. So here we clearly have a geometric kind of like thing going on in this question, right? So look back in your notes about the guidelines for related rates. And the first thing that you'll see that suggests that we do is to draw a picture. So here's, or a diagram, right? And label it. So here's the bacteria. They start out somewhere, on the petri dish, and then they expand out into a circle. So there's my bacteria. They're green because they're, I don't know, like bacteria E. And so let's see, we have this relationship. We know it's a circle because of this concentric rings. And it also tells us it's a circular area. Right, so they're like all taking up like this entire area here. So I might label this as like, let's let A equal the area of the circle. So the 2D space that the bacteria here are taking up. We also have in this question a variable that's changing, which is the radius. So the radius of this area would be from the center out to the edge. Let's call this maybe little r for radius. Now, as time goes on, right, the area that the bacteria are taking up is it's growing outward, right? So like, we don't have a formula for the area in terms of days or in terms of time. We also don't have a formula for the radius in terms of days or time. We don't even know where it starts. We just know that every day the area is changing at a rate of 3 square centimeters. So it's gaining 3 square centimeters every day. So by the time the radius is this big, there's a lot of area that's going around the sides here. So I don't know, the next day, maybe the radius is out there. And we want to know that when the radius has reached 4 centimeters, how fast is the area changing? So again, we don't even need to know the time. We don't even need to know the days that we are looking at here, because of the fact that we have a formula that relates area and radius. Okay, so we know that the area of a circle is pi r squared. And that's all that we really need in order to help us. So, okay, so A equals pi r squared. So this is our formula that we're going to be working with. Let's try to extract out of the question some rates that we know and also maybe a rate that we're looking for. Okay, so we didn't do this in the previous profit question, but I would suggest maybe doing something like this in general. So I would make like a known or given column, and then also make a want column. So what are the things that we know? The first sentence doesn't really tell us much about anything in particular. It just sets up the context. The second sentence says the circular area is increasing. Here's a good verb that is talking about a rate, right? And also says at a rate of 3 square centimeters, and then per day. That's a rate over time. So there are some keywords here, but also try to visualize. Don't rely too much on just keywords and stuff like that. But increasing is a good indicator, and then the per day, and of course at a rate. So the area is what's increasing at a rate of 3 square centimeters per day. Okay, so that rate of change will be dA dt. The rate of change of the area is increasing, so it'll be 3 square centimeters per day. Okay, so I put that under the known or given column. Then the next sentence says, when the radius of the outer ring is 4 centimeters, at what rate is the radius of the circular area changing? So at what rate is the radius changing? The rate of the radius, that symbol is dr dt. So that's what we're looking for. But we want this at a particular point in time. We don't know the time in terms of a time measurement, like days, but we do know that at the time we're looking at, the radius is equal to 4 centimeters. Now that's only at one point, right? It's smaller than that beforehand, earlier in a day, and then after that it gets larger. So this is not always 4 for the radius, but we want dr dt when the radius equals 4 centimeters. Okay, so, well, we've got our formula, a equals pi r squared, and we want to find the derivative of that now to get all of our rates involved. We need a formula that relates dA dt and dr dt. Okay, so we'll start with a equals pi r squared. Now we want to differentiate this with respect to time on both sides. Okay, so the derivative of a would be 1, but then everything is implicit with related rates or with differentiating with respect to time, right? A is not a little t. So this gets a 1 times dA dt, which is the rate of change of A. Then this, on the right-hand side, we've got a pi here. Remember that this is a constant multiple. And so when we differentiate pi r squared, the pi will just constantly multiply in the front. We differentiate the r squared, that gives us 2r, but then we have to multiply this by the rate of change of r, which is dr dt. And now just cleaning this up a little bit, we'll just rewrite this as dA dt equals 2 pi r dr dt. Okay, now this here, this is the amazing related rates equation. So we started here. We know that from way long ago, right? Just relates very statically the radius and the area of a circle. But from that, we have this really dynamic equation that comes out of this, that the rate of change of the radius is related to the rate of change of the area if we just know the radius and the rate of change of the radius, which we happen, oh, well, at least we know opposite, right? We're looking for dA dt. We have, oh wait, we're looking for dr dt. We have dA dt and we have r, so we'll be able to plug in and solve for dr dt. My confusion is a good reason why we make this chart here, so that you don't get too confused. There's a lot to keep track of. So once we find our related rates equation, and again, it's really important to know that that's what this is. So this is the related rates equation. Okay, now what we can do is substitute in the variables that we know. So we know that dA dt is 3. We want dr dt when r is 4. And so it looks like now we'll have an equation where we can solve for dr dt. So I would just do 4 times 2 first, so that's 8 pi. And then to solve for dr dt, we'll just divide by 8 pi. Okay, so that tells us that dr dt will be 3 over 8 pi. I don't know, let's see what that comes out to be. If you do plug this into your calculator, make sure you have parentheses around 8 pi in the bottom. Otherwise, it will just think you're dividing by 8. And this is about 0.12. We all definitely need some units on this. So the R is measured in centimeters and T is measured in days. So this is centimeters per day. And that's what we're looking for. So at the moment in time when the radius has hit 4 centimeters, the next day after that, the radius will increase by about 0.12 centimeters. Pretty cool, right? We didn't have to get time involved at all, which is what is really neat about this whole idea. So this was example number 2. I've got 3 more for us to look at. So tune into those videos and I will see you then.